In this video, we're going to focus on leaving group stability. Now, it's important to understand this concept because this is a very common test question that you'll see for your next exam, if you're studying for an exam in this topic. Now, let's say if you have 2-bromopentane, and let's compare that with 2-chloropentane. A typical test question might ask you something like, which one of these two substrates will work better in an SN2 reaction? Now, the carbon-hydrogen framework is the same. The only thing that's different is the leaving group. So in order to know which substrate will work better in an SN2 reaction, you need to know which is the better leaving group. Is it bromide or chloride? For the halogens, here's what you need to know. Leaving group stability increases towards iodide. Now you might be wondering why. Iodide is it's a more stable ion. It's a weaker base than fluoride. Weak bases make good leaving groups. Strong bases are bad leaving groups. So a good leaving group will have the ability to stabilize the negative charge very well. In the case of fluoride, fluoride is a small negatively charged ion. Iodide is a much more bigger negatively charged ion. And because of atomic size, because it's so much more bigger, it has more surface area in which it can diffuse that negative charge. So here, the negative charge is more concentrated in a smaller region of space, but here the negative charge is spread out over a larger region of space. And that's why this is a more stable ion and therefore a better leaving group. There's a video that I created which is entitled Stability of Negative Charges. I recommend watching that video because it'll help you to see the factors that affect the stability of negative charges. And when you understand that, you can determine which leaving groups are going to be good and which ones are going to be bad. So the more stable the ion is, the better the leaving group will be. Now let's look at some other examples. So here we have 2-fluoropentane, and let's compare it with 2-aminopentane. Which one is the better leaving group? Fluoride or amide? What would you say? So this is fluoride and this is NH2-, which is amide. Which one is more stable? Which one's the weaker base? Fluoride is a weaker base than the amide ion. That's a strong base. And you can look at the pKa values. The pKa for HF is around 3.2. The pKa for the conjugate acid of NH2-, which is ammonia, that's around 36 to 40. So NH3 is the weaker acid, HF is the stronger acid, which means F- is the weaker conjugate base, NH2- is the stronger conjugate base. So the good leaving group is going to be the weaker base. So fluoride is a better leaving group than NH2-. Now, the halogens chloride, bromide, iodide, those are good leaving groups. Fluoride is considered a poor leaving group. NH2 is even worse. So this is a very, very bad leaving group. It's very difficult to get that NH2 group out of that carbon chain. So in this example, fluoride will be considered a better leaving group than NH2- because it's a weaker conjugate base, it's more stable. Now, in the video that I've created, the stability of negative charges, the reason why fluoride is more stable than NH2- is due to electronegativity. In the periodic table, we have these elements: carbon, nitrogen, oxygen, and fluorine. When you're looking at elements in the same row and you're wondering, is it better to put a negative charge on carbon, nitrogen, oxygen, or fluorine? It's going to be fluorine because fluorine is more electronegative. Therefore, it could better handle a negative charge than nitrogen or carbon. So putting a negative charge on the fluorine creates a more stable situation than putting it on nitrogen. So that video, Stability of Negative Charges, it covers a lot of things like atomic size, electronegativity, hybridization, the resonance effect, electron delocalization, solvent effects, aromaticity, all these different factors that can affect the stability of a negative charge, which is relevant for leaving group stability. So here's a question for you. Which one is the better leaving group? OH or OH2 plus? Now, if we were to remove OH, we would get hydroxide. If we were to remove OH2, we would get water. Hydroxide is clearly a stronger base than water. Water is neutral, but it's the weaker base relative to hydroxide. So water is going to be a better leaving group than hydroxide. So this is how you can turn a poor leaving group into a good leaving group. So this is a bad leaving group. But if you add an acid to it, if you add a proton to it, you can turn it into a good leaving group. The same is true for NH2. Here we have an amine. This is a bad leaving group. But if we were to add a proton to it, we could turn it into a better leaving group. Now, this is not as good as water or chloride, bromide, and iodide, but it's a lot better than what we have here. So this is like an okay leaving group. It's not necessarily a bad leaving group, but it's like okay. Now consider these three examples. Which one would you say is the best leaving group? And which one is the worst? So we're comparing OCH3, we're comparing this and that. Now if we take off OCH3, we're going to get methoxide, which is a strong base. If we take this group off, we're going to get acetate. Now in both cases, we have a negative charge on the oxygen. However, we know that acetate, the oxygen in acetate, that negative charge can delocalize among these two oxygen atoms. So it's shared among those two oxygen atoms, which makes this a more stable situation. This is considered a strong base. This is considered a weak base. Now this one, here we have a sulfur with two double bonded oxygen atoms and a CH3. So the negative charge can be shared among 3 oxygen atoms as opposed to 2. So this is going to be the best leaving group. This is the worst, or we could say it's a bad leaving group. This one is okay. I mean, because this oxygen is still stabilized by resonance, so it's a decent leaving group. But this one is a very good leaving group. The negative charge is stabilized by resonance, and putting a negative charge across 3 oxygen atoms will create a much more stable situation than having the negative charge shared among 2 oxygen atoms. So that's basically it for this video. So now you know how to determine if you have a good leaving group or if you have a bad leaving group. So remember, bad leaving groups, they are strong bases, and the negative charge on those leaving groups, they're not stable. A good leaving group are weak bases, even better neutral, and the negative charges on those leaving groups, they're stabilized by something, whether it's a resonance, electronegativity, atomic size, or something else. So remember, weaker bases make better leaving groups, stronger bases make bad leaving groups. Now, for those of you who are interested in downloading that practice test, here's how you can do it. So if you go to patreon.com/mathsciencetutor, it'll take you to my Patreon membership page. Now, to get this particular worksheet, you need the level 4 membership. This is where I have my worksheets for final exams and practice tests. Once you sign in, you'll see something that looks like this. And if you go to organic chemistry posts, you're going to get access to the extended versions of my organic chemistry videos. You've seen the free versions, which could be, for a typical video, like 20 minutes long. The full versions could be an hour or 2 hours long. Some are even like 4 hours long. But you could find the links to the direct link to the extended version of my YouTube videos in the description section of the referring video on YouTube. So if you're taking your second exam, and if you're studying SN1, SN2, E1, E2 reactions, I recommend viewing this one. I think the free version is like 30 minutes long on YouTube, somewhere around there. The full version is an hour and a half long. This will give you a good overview of SN1, SN2 reactions. But here's the practice test that you can download. It has 77 test questions, and I've put as many variations of problems that you might find on a typical exam for this topic in this particular document. Now, this is the video that has all of these questions, but has the answers as well. But for those of you who prefer to get a printout and maybe work on this while you're at school or something, you can check this out when you get a chance. So you need the level 4 membership to get this document, but the level 3 membership to access this video. So feel free to take a look at that when you have a moment.